So, welcome to week 1, a photonic integrated circuits tutorial. So, I am Mukta. I am a PhD student who works at SENSE. I work with Professor Shankar in Photonic Research Lab. And so the idea of these sessions is basically we discuss some topics covered in the lectures, do certain problems related to those topics, and then even discuss the previous assignment problems. So since this is the first week, we won't be having any previous week assignment problems. So we'll do the first two things today. Okay. Yeah. So let's start with the discussions. Okay. So photonics means basically study of light, right? So light and how objects interact with light. So if I want to study a simple lens, there are many ways in which I can study the optical behavior of a lens. So here I am showing four different images of four different type of ways in which we can model the behavior of a lens. So in the first image, as we can see, there's an object, and then there is an image that is formed. So this image we are forming by simple ray tracing methods. So this type of optical phenomena we call it as uh, you guys might already know this. We call it as ray optics. So here we simply just know the refractive index of the lens, based on which we will predict the focal length, and then based on the focal length of the lens we can trace the rays so as to generate an image. Yeah. So that is basic ray optic phenomena. Similarly, can you guess here why we are getting different images for different types of light being emitted by the object? So for different frequency of light, I am getting a slightly shifted image for blue light and for red light. So what is this phenomena called? Anyone of you wants to answer? So this formalism is still ray optics itself. However, something has changed here. So for different frequencies of light, I'm getting different images.
Is it chromatic aberration?
Uh, Chromatic aberration, like more simpler terminology will be just dispersion, right?
Yeah.
So all we are seeing here is a change in refractive index for different uh, frequencies of light.
Yes. Yes. Yeah.
Yes. Yeah, chromatic aberration, we can call it for a particular case of lens, but in general, the idea is of dispersion.
Yeah. The cause is the dispersion and the effect is the chromatic aberration.
Cause is the dispersion and effect is the exactly.
Yes. Yes. Yes.
Yes. Thank you. And so here, in this case, in the third case, you see that there's an object here, and it is emitting light. And now the lens is so small that it is of the order of the size of the lens is of the order of the wavelength of the light. And so I am seeing a slightly blurred image on the other side. So how can I explain such a phenomena? So just ray optics is valid for when my lens is a large object, but when I'm going to smaller length scales, which phenomena should I use to explain such an effect? Which formalism should I use to explain such an effect? So it's basically wave optics, right? Or electromagnetic wave optics. So this is the one which we will be going into detail. Uh, yeah. So there is another formalism as well, which so in this case, say now my light source, I am dimming it so much that at the time only one or a particular number of photons are only emitted, and then that photon goes and goes to some place on the image. So we cannot predict where exactly it goes, but we have a probability distribution of uh, of the places where the photon might hit on the screen. So then this we can model using quantum optics. So yeah, so we'll be going in detail for electromagnetic wave optics. So the yeah, uh, so the concept of electromagnetic waves came with the Maxwell's equations, and so let's briefly recap what were the Maxwell's equations. Yeah, so can you guys help me fill in these equations? So the first one is basically, so H is my magnetic field amplitude. So basically magnetic field. E is electric field. So if I have magnetic field and I take an area integral. So say if I have a closed area and then there is some small element of area here on this sphere. So imagine this to be a sphere and there is a small area element here. So the magnetic field dot product with the area vector is H dot dA. So now if I sum this up over the entire sphere, what should I get? So this is the Gauss law of magnetic field, right? So if I sum up all the magnetic field that is coming out of this sphere, what do I expect here? Zero, right? So because we don't so whatever are the field lines that are coming out of the sphere, there will be equal number of field lines that are coming in because uh, not because this is a law, and that basically says that there are no magnetic monopoles. So uh, similarly, if we have an electric field, the electric field Gauss law states that the area integral over a sphere of electric field dot, so the sum of all these E dot dA elements will always be equal to sum of all the charges. So in the case of electrostatics we have electric monopoles called the charges. So that will be sum of all charges upon the permittivity, right? So these are the two Gauss laws, and then we have H dot dl. So if I have a loop, okay, and then if I do a magnetic field integral along this closed loop, so that will always be equal to the amount of current that is uh, the current that is passing through the loop. That is basically just mu naught times I plus. So magnetic field is not just produced by the current, right? So even if there is a change in the electric flux, that will also induce a magnetic field in along the loop. So that is given by mu naught epsilon times del phi E by del T. Yeah, so phi is nothing but the change. Phi is electrostatic flux, and this term tells us the change in electric flux through the loop. Similarly, we also have a similar formula for E dot dl. Yeah, so basically change in electric field will produce magnetic field, change in magnetic field will produce the electric field. So to more formally define these fluxes, the electric flux is nothing but surface integral of electric flux density. So that is D. So this D is nothing but so flux, by flux we think of E dot dA, but this flux also depends on this epsilon term. Epsilon is the permittivity. So the electric flux depends on the material property. Similarly, there is magnetic flux. Magnetic flux is given by magnetic flux density times dA, and where magnetic flux density is permeability times the magnetic field. So these are just the formulas. I just wanted to write the Maxwell's equations formally before starting. Okay. So that brings us to the first problem. The permittivity of a medium is a function of position or spatial location. Like the epsilon is given to be epsilon of r. So what will you call such a medium? Is it isotropic, homogeneous, anisotropic, or inhomogeneous? I hope I'm audible. So yeah, let us understand all these terms one by one. So yeah. So what is isotropic? Isotropic basically means that if permittivity along all the given directions is same, then we call it isotropic. Similarly, anisotropic means if the permittivity along all given directions is not same. So it is different along x direction, different along y direction, and similarly something else along the z direction, then it is anisotropic. But in this case, it's not just that the permittivity is different along the different directions. It is a function of the position. So it might happen that uh, I have uh, say I have some material that is denser in certain regions and then rarer in certain other regions, or for some other example, you can think of it like a grating leg structure. So in this grating leg structure, um, so my refractive index or the permittivity is different in this region compared to this region compared to the next region. So it's a function of position. So such a material is called an inhomogeneous material. So homogeneous material means everywhere the permittivity is same. Inhomogeneous material means it is different at certain locations. So similarly, now if my permittivity is given by such a tensor, so then it is different in different directions. Then I call it anisotropic. Yeah. So in case of optical fibers, so this problem asks us that the figure shows three types of optical fibers. Which type of optical fiber has an inhomogeneous core? So first let us see all the three types of fibers that are given here. So in this case, the core has a higher refractive index compared to the cladding. However, the refractive index remains same throughout. So this is called a step index fiber. So since the refractive index of the core is the same throughout, so it is not, so it's homogeneous. So it's not inhomogeneous. Similarly, graded index fiber. So graded index fiber means this index doesn't increase abruptly. The change is not an abrupt change, but it's more like a gradual change. So in this case, the core is actually an inhomogeneous core. So why we use this graded index fiber is primarily because if we are using a step index fiber, the different modes. So if my light enters at this angle, it will have to traverse this path, which is longer than if my light is entering at say some shallower angle. So like the if I have a single pulse, the pulse will get broadened at the end because different components of light are traveling different paths, so they will be traveling at different speeds through the fiber. However, in a graded index fiber, so even if my light is going at different angles, finally the path it follows, the speed difference between different angles is relatively lower. So because of that, the broadening is minimized. Okay. And then there is single mode fiber. Single mode is again just like step index. However, the core region is quite thin, so that can occupy only a single mode. So this is also a homogeneous case. Okay, so the third problem is a bit involved. So we have to derive the wave equation for electric field from Maxwell's equation in free space. So let me just write down the Maxwell's equations first. So before I had just written them down for a material medium, now I have to write them in free space. In free space, uh, I will write them in the differential form. So there are two curl equations and two divergence equations. The curl equations I'll write down first. Uh, yeah. Then the divergence equation.
Madam, generally the optical fibers that we get, multimode fibers,
Huh.
their step index or gradient index. Generally, whatever we get from market like Thor Labs or
Uh, I'm not sure actually. Uh,
any type. It may be any type.
huh.
Okay, okay, ma'am.
Mm. Yeah, I'm not sure. Okay. Yeah, so I wrote down the equations, Maxwell's equations. Now we want to derive the wave equation from this. So, so one way of doing it is just take the curl of the first equation. So, yeah. So all these fields are continuous. In real world, we don't have abrupt changes in electric and magnetic field. So that gives us del cross minus dou by dou t of mu h. So just as I said, this is continuous. I can bring this dou by dou t outside and the del inside. And then del cross h is nothing but dou d by dou t. So that will give me dou square d by dou t square. And then there is a mu also here. So yeah, so then I have this as del cross E. So I'll just convert this D to E so that I have everything in terms of E. That will be nothing but minus mu epsilon. So remember that D is nothing but epsilon E. So assuming that my epsilon is not changing with time, yeah. So now I have everything in terms of E. However, this still doesn't look like wave equation because of the left hand side. So we have to simplify the LHS. Just a minute. I think someone is trying to join the meeting. Yeah. Yes. So we have got till here cross del cross E is equal to minus mu epsilon dou square E by dou t square. Now we need to simplify this LHS. This we can easily do by from this identity. So del cross E, I can write it as del into del dot E minus del square E. So this is just a just from calculus. Right, so now can I put this del dot E equal to 0 from Maxwell's equation? So in Maxwell's equation we saw that del dot D is given to be 0. So in general it might not be true that del dot E is also, so it can happen that this epsilon, like we saw in the previous case, it might depend on the position, or it might change with the position, or yeah. So so then this expansion might become del dot E times E plus epsilon times del dot E equal to 0, and then then we can simplify to get del dot E equal to minus of, yeah, but all this we have to do only in the case when our epsilon is varying. But we are the we started with assuming that we are in vacuum. So for vacuum we can just assume this del dot E to be equal to 0. So basically the epsilon is constant in vacuum, which is equal to epsilon naught. So my del dot E will become 0, and then I have my wave equation, del square E equal to mu, since this is vacuum I'll write mu naught epsilon naught del square E by dou t square, dou square E by dou t square. Right, so this is a so now this has taken the form of a wave equation, and the speed of the wave is given by, so here 1 by v square is nothing but mu naught epsilon, which implies v is equal to 1 over root of mu naught epsilon. Right. So is it clear till now?
Yes, ma'am.
Okay, thank you. Yeah, so next, the problem says a light wave of wavelength 2 micrometer is directed in the xy plane at 45 degrees. So now they have given us that the wavelength of the wave is 2 microns, and yeah, they have also given us the angle, and we have to find the magnitude and direction of the k vector. So yeah, first of all, we have not yet discussed what is a k vector. So for any wave, any generic wave, uh, that is denoted by a wave equation, uh, the wave we can write it as, so first let us try to pictorially see a wave. So if this is my position and this is the magnitude of the wave, then it is varying, uh, either it can be sinusoidal, or yeah, there can be a certain phase, but it goes up and down with position, and also it travels with time. So uh, if we see the time see this wave with time, it will move either in the positive or the negative direction. So every wave can be represented by a wave vector which has some amplitude or magnitude times an oscillatory response in space and time. So you can verify that this is actually a solution of the wave equation by just simply putting it in the wave equation. So the wave equation is del square square minus mu epsilon dou square psi by dou t square equal to 0. Right. So we can just put it in this and see what are the conditions that the k and omega should satisfy, so that this equation, the oscillation equation that I just mentioned here, is actually a wave equation. So I'll just put it for now. So del square psi is psi naught e power So I'm differentiating it twice in position, means I'll first take the omega t term out, and then there will be I k square times e power I k dot r. Similarly, dou square psi by dou t square will be mu epsilon times dou square psi by dou t square is equal to, again this e power I k dot r I'll take outside, then I will have I omega square over I omega t. Now these both are equal, right? So if these two are equal, what relation does it give us? So these terms are just repeating, which means I can basically say that k square is equal to, oh, I forgot some terms. I forgot the mu and epsilon here because I put it here, right? K square equal to mu epsilon times omega square, right? So from this, what is the magnitude of the k vector? Magnitude of the k vector is nothing but omega times root mu epsilon. Or if you remember, this root mu epsilon is nothing but 1 by v, or velocity of the wave, that is nothing but omega over v. Okay, so now that we know what is k, can you uh, can you now find the magnitude and direction of the k vector? Sorry. So let's try to do it together. I'll just take a new slide. Right. So I have a wave. Okay. Some wave. And then they have told us that the wavelength is 2 micrometers. So this distance is 2 micrometers. Right. So now, in order to find k, so we need to understand that the psi at this point is equal to the magnitude of psi at this point. So if I just name this point as r, and this will be r plus lambda. Lambda is 2 microns. So my this psi from this simple relation we can see that basically means that e power I k r will be equal to, because the other things are same, right? Psi naught and e power I omega t remains same, so that we can cancel. So we'll get e power I k r equal to e power I k r plus lambda, right? So what does that mean? That so this I can just expand as e power I k r times e power I k lambda. So that basically means that e power I k lambda is equal to 1. So from this I can write k lambda equal to 2 pi. Basically k lambda can be anything, any multiple of 2 pi, right? So it can be 2 pi, 4 pi, 6 pi. But why am I writing here 2 pi? So that is primarily because the wave vector here has the same magnitude as so psi has the same magnitude here and here, but it does not have that same magnitude anywhere in between, right? So if I write 4 pi, so when I'm writing it 2 pi, k will be nothing but 2 pi by lambda. If I would have written 4 pi here, then that would have basically meant that how do I say, that would have made this condition valid even for lambda by 2, but that is not valid for lambda by 2, so I am forced to write here 2 pi. So uh, although I am saying that this is the constraint, there is another inherent constraint that this is not true for uh, any number here smaller than lambda. So based on all these two constraints, I am writing here k lambda equal to 2 pi, then k equal to 2 pi by lambda. So from this we can easily find out the magnitude of the k vector. That will be basically just 2 pi over 2 into 10 power minus 6, and then we can solve it to get the value. Now next part is the direction of the k vector.
This can you please repeat, ma'am? Actually, why we cannot write 4 pi? The other constraint that I did not understand.
So yeah, if you write here 4 pi, that what will happen? Let's see. So if I write k lambda equal to 4 pi, that would mean that lambda equal to, k equal to 4 pi over lambda, right? So uh, um, and if I do e power I k r plus lambda by 2, yeah, now if I do e power I k r plus lambda by 2, that will be equal to e power I k uh, r plus e power sorry I k r plus e power I k k lambda over 2, and I k lambda over 2 is nothing but k is 4 pi over lambda, right? So e power I k lambda 2 is e power I into 2 pi. So uh, this will become e power I k r plus e power I into 2 pi. Is this okay?
It's
Yes.
into or plus, ma'am?
Into sorry. So now this is 1, right? E power I 2 pi. So now my e power I k r plus lambda by 2 became equal to e power I k r. But that is not true, right? See, here
Yes.
at lambda by r plus lambda by 2, it is not equal. So that is the other constraint I was talking about. So I want uh, the constraint, I am not able to formulate it correctly. So basically it should not be true for any uh, value less than lambda. That is the other constraint. So I cannot put
Understood.
anything 4 pi here. Thank you.
Understood. Understood.
Uh-huh. Yeah. So the next part is the direction part. So that is pretty easy. They have told us that it is directed at 45 degrees. So we just found the magnitude of the k vector. Now, if I want to find the entire k vector, it has to be something of the form k into x cos theta. So it's directed at 45 degree in the xy plane. So this cos theta will, so I'll just write down first y sin theta, right? Or you can write out I cap and j cap also, that is fine. So this k we already found out, that is 2 pi over lambda times, since this is 45 degree, cos theta and sin theta both will be nothing but 1 by root 2 x cap plus y. So this vector will completely define the uh, will basically give the both magnitude and direction of the k vector. So I guess in your assignment problem they have also given a similar problem, and they've asked you to write the direction of the k vector. So since they have said to write in uh, like so how do you write the direction is, I would suggest you just write this number for now. I'll talk with Professor Shankar and like ask to clarify the question again. So magnitude will be clear, but to write the direction, I would suggest that you don't write the vector part, like this part. Just write the x component or y component of the k vector. Is that okay? Like the question is a bit ambiguous, so I was telling that you can write this number. So this is a different question. Uh, the corresponding number for that question. Is that okay?
Okay. Okay, ma'am.
Okay. So let's move to the next question. Phase and group velocity for a material exhibiting yeah. So now they have given us the relative permittivity of the material. That is this. A broad class of non-magnetic dispersive media exhibit relative permittivity to be so much that varies as a square of frequency over a narrow range of frequencies centered for okay what for this media we presume this. So they have given the relative permittivity relation. From this we have to find the phase and group velocity for a sinusoidally varying wave in this material. So they are basically asking us the phase velocity and the group velocity. So yeah, just to recap, the phase velocity. So if I have a wave like this, so a single frequency wave. Uh, so if I just see the frequency spectra of the wave, it will be just a single frequency. This is mu frequency versus amplitude. Okay, so such a wave, I can imagine it to be a sinusoidally varying signal in time. So in such a wave, the phase velocity is defined. So if I'm standing here, what velocity I should travel in the in this time direction, so that I see this point all the time in front of me. So that is the basically the idea of phase velocity. So uh, so the way you get the phase velocities, if I so I should keep seeing the same phase point. That means that my phase has to be constant. So this term in the wave equation, so there will be some amplitude times this term, right? So I want my this phase term to be a constant. That basically means that kx minus omega t should be constant. Different constant, but yeah. So this should be a constant, which means my uh, I should have written z because here they are denoting it as z. So this basically means that my z should be equal to omega t over k plus some c. So now my velocity of this particular phase will be omega over k. So that is basically the phase velocity. Vp is omega by k. So if I have a single frequency wave traveling in my medium, the velocity at which the phase travels is the phase velocity. So then what is a group velocity? So in most general situations what happens is we cannot have a single frequency of light, we will have some distribution around that frequency. So then there are multiple frequencies traveling in the same medium and then they will interact. So because of that there will be a there will be a uh, an envelope like thing that is created. So imagine that I have only two frequencies. So starting from single frequency, let us say I am going to two frequencies very closely spaced. So if this is omega, this is at omega minus delta omega, and this is at omega plus delta omega. Okay. So if I try to describe the behavior of omega minus delta omega and omega plus delta omega at the same time, I'll see instead of a clean amplitude versus time wave, I'll see a wave that varies like this. So it has a phase component that is oscillating with uh, with frequency omega. So the frequency of this thing is omega, but in addition, it is also having an envelope. So the frequency of the envelope is uh, so yeah. So that is given by delta omega. So let us see it in proper detail. So see, I have two frequencies, omega minus delta omega, and this is omega plus delta omega. So if I have these two frequencies, uh, even my wave vectors will be two different, right? So say this, I am calling it k minus delta k, and this one I am calling as k plus delta k. Then for these two frequency lights, the total electric field E will be the field component due to this one plus the other one. So then yeah, how will I write E1? Say it's just a cos wave. I will write it as E naught uh, cos omega minus delta omega times t minus k, sorry, this k plus delta k times z. Right, so this is my E1, sorry, minus. Then E2 will be similarly E naught cos omega minus delta omega yeah, correct only, times t minus k plus delta k times c. So basically just I am writing E equal to E naught cos uh, omega t minus kz. Okay. So using this relation, I am writing it for E1 and E2. E1 has frequency as omega minus delta omega, and k minus delta k as the k vector, and E2 has omega plus delta omega and k plus delta k. Okay, so if I simplify this using the cos A cos B relation, yeah, then I will like just by using the trigonometric relations, I can simplify it to get something like this. So if you see now, this is like uh, so for a fixed phase point, like for a this you can think of it as, if this I think of as some amplitude that is varying with this that is varying as a wave with this component. So there are two waves now. So one is because of this omega and this k, that is traveling at, so that is traveling at a velocity of omega over k, that is the phase velocity, and then there is this envelope. So this envelope is traveling at the velocity of delta omega by delta k. So we can see here, right? So the velocity at which this phase is traveling is omega by k, and the envelope is traveling at the velocity of delta omega by delta k. So that again we can derive similar to this. So if I just assume that this has to be a constant, then I'll get this as my velocity. So, so is this group velocity? So the group velocity that it is defined as, so in general we won't have just two frequency components also, we'll have multiple frequency components around this uh, wavelength frequency omega. So the group velocity is defined as delta omega over delta k, so the width where limit delta omega goes to 0. So that is the definition of group velocity. So yeah, so I was just trying to motivate where this definition came from. Is that okay? Now that you know the definition, it is quite trivial to do the problem, right? So yeah, I'll just do it. So first we have to find the phase velocity. So Vp is nothing but omega over k. So for doing this, we first need to find what is k. This we I think did previously, right? K is nothing but omega root mu epsilon. And now epsilon is given by, uh, yeah, I'll just do it. Omega is root of mu naught epsilon r. So from there we'll get omega root of mu naught epsilon naught root. Now epsilon r root is nothing but root of k times omega by omega naught. Since I'm taking root, the square is gone. So that is my k. So from this I can get Vp. Vp will be nothing but omega by k. So I will get, finally I will get omega naught over omega root of k mu naught epsilon naught. You can verify this. Similarly, now I have to find Vg, that is the group velocity. Group velocity is nothing but dou omega by dou k. So yeah, since I know k with respect to omega, so I'll just do an inverse. Dou k by dou omega inverse. So that is nothing but k is this. I'll simplify it to omega square by omega naught root k mu naught epsilon naught. So that will become 2 omega into all these things. Yeah. So yeah. So if I just compare it with this and write it in terms of wave vector k, so I will get this equal to, so this is the constant k, okay, this is this k. So I now I want to write it in terms of the wave vector k. So that will be equal to just frequency omega over 2k, right? Oh sorry, there is an inverse here. Now it will be equal to omega over 2k. So that is, so we know that omega by k is Vp, right? So that will be half of Vp. So the group velocity is half the phase velocity in this case. Okay, so yeah. What is the wavelength of light in a medium of refractive index 3 if the free space wavelength is 1550 nanometer? Yeah, so this is pretty easy. The refractive index is defined as the speed of light in vacuum, sorry, to the speed of light, the phase velocity of light in the medium. So from this we can get the wavelength. So we know that k equal to omega root mu epsilon, right? Uh, so yeah, we can simplify this further. C is nothing but 1 by root of mu naught epsilon naught. Vp is nothing but root mu epsilon. So, yeah, so assuming that my uh, mu is constant over most of the optical frequencies, so I will, just to simplify the things, I'll write it as root of epsilon over epsilon naught. And my k is omega times root of mu epsilon. So that will be omega times root of mu naught epsilon naught, right? So this is nothing but my refractive index. So this will be, if I just call this some k naught, it will be k naught times refractive index. Yeah, so now what they're asking, wavelength of light in medium, if free space wavelength is so much, then just k I have to convert it into wavelength now. So wavelength of light in medium, if I just denote it by lambda prime, this is 2 pi over lambda times n. 2 pi get cancelled, which implies lambda prime. So wavelength in a medium is equal to wavelength in free space upon n. N is the refractive index. So that's it. We can just substitute and get the answer. So that is all for today. Yeah. Do you guys have any questions? Like, even if there is something in the lectures that you want me to cover, or yeah, I can come prepared in the next tutorial based on that. Like if you have any doubts in the lectures or something, or in today's class.
That group velocity phase velocity relation from which book you have shown that, ma'am? That
Uh,
beating
the
of waves you have shown,
Yeah,
no?
yeah, that image, right? This
Yes.
I took from Clifford. Let me check once. Yeah, it was Clifford. It is there in one of the reference books, like Fundamentals of Optoelectronics by Clifford Pollock.
Okay, ma'am.
Okay. Okay, then I'll stop the screen share, and yeah, all the classes will be available, like the recordings will be available to you guys. Yeah, on the NPTEL site itself. Okay, thank you guys for attending, and we will meet on next Friday.
Thank you, ma'am.
Thank you. Thank you, Shanivas.